I'll try to stay out of your guys' way while you copy this down. I'll try to stay out of the way so you guys can copy this down. How many people can see it? How many people can see on the board? How many people can kind of see the board? Okay, well, I'll read it, but just try, do your best to try to copy what's there. Just be Egyptian scribes. Be Egyptian scribes. Even if it looks like hieroglyphics, write down what's there. Write down what you have that's there. All right, guys, wherever you're at, just stop right now. Just stop writing. Today we get kicked out of the helicopter. The first thing I'm going to do is I'm going to go and share a file that I'm going to put up on Canvas. So I'm going to go into the tunnel over here. Hopefully you can still hear me. And I'm going to share a file. Can you guys see this? Can you guys see this file? All right, how many people can see it? How many people are seeing the file? Okay, what's the title of this? Okay, now listen to me. Whenever you say in a proof, math is proof, you're going to be doing proofs. Whenever you say in a proof, you're using the algebra of the real numbers, then you're using these properties. So let's run through these just quickly. The first one is what? Number one is what? Closure. Now again, you guys aren't used to thinking this way. A real number plus a real number is a real number. It's not something we prove. This is like our Bill of Rights of the real numbers. This is something that we assume. We also assume that A plus B, that real number is the same thing as, and that's called the commutative property of addition. How many people have heard of these before? Okay, this is your commutative for multiplication, your associative property. It doesn't matter which way you associate, as long as you don't change the order, you get the same real number. This is something a lot of you guys don't know. There's a number called 0 that doesn't change a real number's identity under addition. There's another number 1 that does the same thing for multiplication. These are the only two real numbers that came to us. All the rest of them are birthed. All the rest of our real numbers are birthed. We're only given 0 and 1. We're told for every real number there's an additive inverse, meaning there's another real number that when you add to that real number, you get 0. Similarly, these multiplicative inverses. This is your favorite property ever. What is that property? The distributive property. Everybody loves the distributive property. So much they want to use it all the time, even when it's not true. Is the square root of A plus B equal to the square root of A plus the square root of B? Is that true? No. Does the sine of A plus B equal the sine of A plus the sine of B? No. Does the natural log of A plus B equal the natural log of A plus the natural log of B? No. So when you have that desire to distribute, and it's not multiplication, cause yourself physical pain. To punish you. So you say, I'll never do that again. Okay, these next axioms are equality axioms. We have a reflexive property, our symmetric property, our transitive property. We have our addition property of our equality, our multiplication property. Then we've got all of our order properties. And then we've got these other things that we can prove. I'll put this up, but when you're using these in a proof, you can say algebra of the real numbers. Okay. Today, we are going to work really hard in talking about what was Hamilton's goal. What did Hamilton want to do? Did I not tell you this? What was Hamilton's goal when he came up with vectors? What was his goal? To come up with an algebra for geometry. Say that. I mean, he was a sick pup. Because they had points. Everybody understood a point. They had the concept of a line, concept of plane, But the idea of adding lines together, adding points, that was unheard of. But Hamilton wanted to come up with an algebra for geometry. And that's where his idea of vectors came from. Okay, I told you guys I was putting a life preserver on you and kicking you out of the helicopter. Here we go. Stand up, stand up, stand up, stand up. You need to stand up, stand up, stand up. Okay, cross your arms, cross your arms, cross your arms, cross your arms. On 3, you're jumping out of the helicopter into the ocean. 1, 2, 3, jump. Okay, splash. Start treading water, start treading water, start treading water. Okay, sit back down, sit back down. Okay, on Friday we're going to talk about the geometry. After Friday, you should be able to do most of the WebAssign. I'm hoping you've already started the WebAssign. Listen to me. You cannot type I, J, and K in WebAssign. It'll tell you it's wrong. I put up an announcement. How many people got my announcement? How many people got my announcement? In that first link, they show you the drop-down menu. They show you how to access the drop-down menu when you're putting I, J, and K. You're putting I, J, and K. Has anybody read 12.2? Has anybody actually read the words in 12.2? Okay, that will help too. That will help too. My job is to teach you proofs. The book doesn't do that. My job is to teach you proofs. Okay, here we go. Here's some symbols that make your notes look smart. So when you go home, show your parents your notes, and it'll be filled with these. And they'll be going, wow, I can't believe you're learning that. You don't have to tell them that this symbol right here, this with a line means what? What word is that? What? Element of. Here's a question, guys. Would you rather write the word element of over and over and over again, or just write that symbol? How many people want to write the symbol versus the words element of over and over again? Okay, this is laziness. S dot T dot in this class is going to stand for the words such that. We're going to be using them over and over again. S dot T dot. This is probably new to some of you. This symbol, which looks like an E that's dyslexic, this backwards E, stands for the words there exists. We're going to write that so many times, you're going to love that symbol because it saves you lots of time. Another dyslexic variable, capital A. It's not a variable, it's just a letter. Stands for the words for every. So you'll get used to it. I'll keep saying it and writing it down and asking you. Okay. Let's read with Dr. Horn. What does that mean? What does that mean? Definition. We're defining our vector space on R3. Say what I just said. This was a magic moment in the 1850s. This was a magic moment. Up until then, all they had were real numbers, which Descartes kind of formalized, really Euler formalized. And then they had imaginary numbers, complex numbers. Other than that, that was all we had. And then Hamilton gave us vectors, a vector space. And then we realized in the early 1900s that vectors weren't enough. And so they came up with matrices, this idea of matrices. How many people have heard about matrices before? And then guess what we found out? Matrices weren't enough. So then Einstein gave us this idea of a tensor. And then guess what we found out? Tensors weren't enough. So our language keeps growing. You guys are going back to the 1850s though, and we're going to talk about a... Help me out. What did I just say that was? A vector space on R3, on three-dimensional space. How many people have to take a class called linear algebra and differential equations? How many have to take a class called linear algebra and differential equations? They're going to extend the idea of a vector space to matrices and other things, cows if they wanted to. Anything that holds the properties that we're going to talk about today. So the words that I'm using are going to help you in your other classes. If you learn them now, they'll help you. If you learn them now, they'll help you.
In other classes.
They'll help you later. So learn them
Now.
now. Okay, okay. Yeah, okay. A vector space on R3 is, can you read the words? Can you read the words?
Is the set of ordered
Triples
of
the form. Okay, so now we're going to introduce a notation for a vector. This represents a bold A. So like if we could highlight it and make it bold, but in our class, we're just going to put a squiggle under it. It's easier than drawing an arrow. So that means what? When you see that A in this class, it's a, say it. It's a vector. It's a vector in R3. It's an ordered triple. So notice these are not parentheses. So this is not a what? That's not parentheses. So this is not a what? It's not a point. This is a vector. It's an ordered triple, A1, A2, and A3. Math is proof. So right now, this is just complete and total crap until we define who A1, A2, and A3 are. Okay, now we've got the word, what's that word?
such that.
Such that. Well, we're going to be lazy, and we're going to write what instead of such that. We're going to write what instead of such that.
S dot T dot.
Yeah, just laziness. S dot T dot. Such that, now you guys help me out.
A1, A2, and A3.
New vocab are elements of the real numbers. Okay, so we know now that a vector is an ordered triple of three what?
Three real numbers.
Three real numbers. Stand up again. Right now, I can already tell you need this. Look at you guys. You're like 3 minutes in, and you're already bored. You're already like, oh my gosh, this is going to go away. This is not going to go away. Slap your face. Say, I must live. I must live. Okay, sit back down. Sit back down. Okay, so what's a vector in this class? If you're in V, then you're a what? I hate you, Dr. Warren. That's not the answer. If you're in V, then you're a what?
Real number?
Not a real number, but I like Ava. Ava, you went after the ball. Everybody else just stood quietly. If you're in V, then you're a...
Set of ordered triples.
Very good, Pierre. Pierre said a set of ordered triples of three what? Of three what, guys? Of three what?
Real numbers.
Three real numbers. Say this after me. If you're in V,
If you're in
then you're a vector.
V, then you're a vector.
Then, of course, I got to go, what the hell's a? Then I got to ask the question, what the hell's a
Vector.
vector? And what is a vector? And Pierre essentially told us it is a...
Set of ordered triples.
It's an ordered triple of
Three real numbers.
three real numbers. Okay, so guys, for the first time, write down a vector. Write down an element of V. Dr. One, don't ask me to do that. No, write down an element of V. Give me an element of V. There's 21 of you. You should be able to write down an element of V. Write down an element. You should have your own unique element of V. There's just so many. There's just so many. Okay, so now I'm going to pick on. Let me see. Okay. There's 21. This is a magic trick. There's 21 people in the class. How many real numbers are there? How many real numbers are there? How many real numbers are there? Eminently many. I am willing to bet that 1/4 of my class, out of all the vectors they could have picked this one. I bet A was equal to 1, 2, 3. Did anybody pick that as their vector? Raise your hands. Raise your hands. Raise your hands. Raise your hands. See, I'm a magician. It's just like David Blaine. Street magic here. This is street magic. Okay, sit back down. Who didn't pick that? Who didn't pick that? Okay, Ava, what was your vector? What was your vector?
1, 1, 1.
Okay. Even lazier than 1, 2, 3 was the vector 1, 1, 1. Okay, but it seems like an important vector. Okay, John, what was your vector?
1, 5, 6.
1, 5, 6. I don't know what that says about you, John, but I like it. I like it. I like it. Okay, how many people realize now what a vector is? How many people realize what a vector is? Are all these vectors? Do they meet the definition of V? If they're in V, they're a ordered triple of, help me out, they're ordered triple of, how many people realize there's an order here? If you switch 3 there, you get a different vector. How many people understand that? There's an order to this. It matters what order they're in. This is not the idea of a combination. It's more the idea of a permutation. The order matters. The order matters. Okay. Read for me. We're here in our definition.
Subject
Addition. So now, guys, we're going to define what it means to have an addition on our vector space. Now you guys help me out. What's that word? Define for
vector A and vector B are elements of vector space V.
Okay, so we're defining, we take two vectors in V, and what we're going to do is we're going to define what it means algebraically to say, now you guys read this.
Vector A is vector A.
We're going to define what it means to add two vectors. We're going to make a definition. Now you're going to hate me, but if A is in V, then A is equal to what? Oh, I hate you already, Dr. Warren. If A is in V, then A is a, we're going back to the same thing again. A vector. You're a vector if you're a? Okay, so since A is in V, then A is equal to an ordered triple, A1, A2, A3, where A1, A2, A3 are real numbers. The vector B is equal to B1, B2, B3, where B1, B2, B3 are real numbers. Now we're going to define a vector plus a vector. Now you're in the beginning, you're at the creation. If you were creating this, and you're like, okay, a vector plus a vector. Vector plus a vector, how would I define that? You don't think some human being thought of this. You act like, this came from above. God said, let vector addition be this. You don't think that, like, wait a second. No, maybe that ingenuity came from above, but was written down by a man. A vector plus a vector. What do you want it to be? A vector plus a vector. What do you think it should be? I mean, right now we've got, it could be a complex number, it could be a real number, or it could be we're in the 1850s. We have the real numbers, we have the complex numbers, and we have our new vectors. A vector plus a vector, what do you guys think?
A vector?
A vector? How many people on board? If we're creating this, how many people are like, let's make it a vector, what the hell? Let's make it a vector. If it's a vector, then it's a what? Dr. Warren, damn it. If it's a vector, then it's a what?
A vector.
Okay, what's a vector? What the hell's a vector? An ordered triple of three real numbers. So you tell me, Dr. Warren, let's make it a vector. So then it's got to be an ordered triple of 3 real numbers. Okay, you guys are the creator. You guys are the creator. You have your vector A, which is these 3 real numbers. You have your vector B, which is those 3 real numbers, and you're going to define your addition to be another set of 3 real numbers. Write down what you're going to define them to be. Write down what you're going to define. If you're going to define them, what would you call that sum vector to be? The sum of those 2 vectors. Write down the 3 real numbers that you would put in those 3 locations if you were just defining it. Now I hope most of you pick the same thing I would pick, but I guess you don't have to. I guess we'll vote here in a moment. We'll vote. Okay, Jack, I'm going with you. Jack, what did you pick that real number to be? What did you pick that real number to be?
I thought it was A1 plus B1.
Oh, Jack, bless you. Because I'd like that. How many other people like that? How many people are with me? Like, say, now here we got to ask, is A1 plus B1 a real number?
Yes.
Yeah, since A1's a real number and B1's a real number. Now remember that thing I shared with you? Do you remember that thing I shared with you? What property, I hate you, Dr. Moore, what property guarantees that a real number plus a real number is a real number? You just saw it briefly. Did it burn into your brain? What property was that?
Additive property?
Close. It was called the closure property of addition. Now look at the door in your room. Look at the door leading into your room. Look at the door. Is it closed or open? Is it closed or open? Is it closed or open? Open. If it's open, then you could get out, right? You could get out. You could get out of the room. If it's closed, then you can't get out of the room. So if it's closed, then a real number plus a real number has to stay in the room of real numbers. Does it make sense why we use the word closed? Does it make sense why we use the word closed? A real number times a real number is a real number times a real number is a because of closure of not addition, but closure of multiplication. Okay. Okay, in a proof, I'm going to let you get away with this laziness. When you're using vector addition that you define, and I'm going to remind you of that all freaking semester long. Oh, I guess we didn't define it. Sorry. Madeline, what'd you pick there?
A is 2 plus B2.
Bless you. That's exactly what I needed. And hopefully, Pierre, what'd you pick here?
A3 plus B3.
And guys, I want you to understand that math is proof. In physics, they don't have the time to lay out a foundation. They write stuff down. Engineering, there's not enough time to even give the physics foundation. So they just give you equations and say, go with it. But in math, we can't wave our hands. Everybody depends on us. They trust that what we build is perfect. There's no other discipline other than maybe philosophy that is under that kind of scrutiny. A vector plus a vector is a vector. You made it so by your definition and closure of addition in the real numbers. Okay, we're also going to define a
Multiplication.
Okay, now you're not going to understand why we call it this in the beginning, but we'll call it a scalar multiplication. So say that.
Scalar multiplication.
How many people have rock climbed before? Okay. How many people have scaled something? Okay, so it's kind of like stretching is what you want to think about. You're stretching something. Okay, we're going to define a multiplication. Now this is going to be bizarre. This is the first time ever in mankind where they took two different objects from two different spaces and multiplied them together. First time it ever happened. Real number times a real number, no problem. Complex number times a complex number, that was done. But here we're going to say a multiplication where who was man of the millennium?
Newton.
Not Newton. Did I not tell you this? I told you this, right, guys? Did I tell you this? Are you guys pulling my leg? You're just wasting the class time, right? Did I not tell you who was man of the millennium? Oh, crap. I got to do this really quick. Okay, what year were you born?
2002.
Okay.
2000.
Oh, God, I'm so old. Okay, so if you were born in 2000, you were born at the millennium, and you don't remember this. But how many people know that they make up, like, man of the year lists? How many people like the most important out of the 6 billion of us, this was the most important man or woman of the year? Okay, in 2000, they had the gall to pick the man of the millennium, which, man or woman, they should have said. Okay, but they called it the man of the millennium in the Time magazine. And guess that would be the man of, not of the year, but the man of the 1,000 years. 1,000 years, the most important man from 1000 AD to 2000 AD. I thought for sure it was Newton. Because I couldn't imagine any other single man changing history as much as Newton did. But in their list, in some lists, Newton's didn't even make the top 10, which really pissed me off. But in the list I saw, Newton was number 2. Newton was number 2. I mean, I guess if you don't make the top 10 of 1,000 out of 1,000 years, okay, Newton was number 2. Do you know who number 1 was on a lot of lists? At first I was pissed. It's like skipping over LeBron James, okay, for being the NBA's best basketball player. You're not picking LeBron, okay, they picked Gutenberg. Gutenberg as a man of the millennium. What did Gutenberg invent? The printing press. Did the printing press change a lot of stuff? Did the printing press change a lot of stuff? I almost have it. In the next 1,000 years, it's going to be the guy that created the internet. It's going to be the guy that created the internet. In your millennium, I think it's going to be the guy that created the internet. I think that's what it's going to go back to. Again, the same kind of idea. Disseminating information. Now, did I tell you about Newton? I was watching Omni. Did I tell you about this? Did I tell you about when I was watching Nova or Omni? I forget which one it was. I think it was Nova. I was watching Nova, which is PBS. Remember, I live in Harrisonburg. There's nothing to do in this town. I was bored out of my skull, so I'm watching Nova. And they had a special on Archimedes. And Archimedes, back in like 200 BC, was this close to calculus. He was this close to beating Newton to calculus 2,000 years, well, not 2,000, I guess 1,700, 1,900 years earlier. And this was the thing that blew my mind. They said if Archimedes' manuscript had not gotten lost, that they would have discovered calculus easily 200 years before Newton. So instead of 1,700, it would have been 1,500. And the statement that followed was absolutely blew my mind. They said that meant that we would have been landing people on the moon in the time of George Washington. That's how much credence they gave to Newton and calculus. This stuff you're learning changed everything. How many people know we landed a probe on a moving comet? How many people knew that? How many people knew that we landed a probe on a moving comet? That's why it pisses me off a little bit about how we're distributing COVID. I mean, this whole last year, I'm like, okay, we can land a probe on a comet, but we are doing this with COVID. You've got to be kidding me. How can this be the same country? How can this be the same country? Well, enough of that. Okay, grid view. Go to grid view. Where are you going to be on Monday? Where are you going to be on Monday? Here, okay. Put your hands on the space bar. And I've got my hands on my space bar too. Okay, now we're all going to promise each other. Let's get ready to say, I promise. Look at everybody's eyes. I promise I will not give you COVID. Say that.
I promise
Okay, now say it again. I promise I will not give you COVID. Okay, say this. I promise I will take my Live Safe app. Sorry, I gotta say this without laughing. I promise I'm going to take my Live Safe app seriously. Say that for the first time. Okay, guys. We are not. If you do not feel well, do not come to class. Are we understanding? Are we on the same page? If you have a temperature, where should you not be? Yeah, you shouldn't be in class. Okay, you've just promised everybody. If you can't taste something, you shouldn't be where? Okay. So I'm filming this. I probably shouldn't have said that. Seriously, I take it seriously every day. Okay, sorry. Okay, back to where we were here. A little commercial break. Okay. For the first time, back to 1850, we're taking two different things from two different spaces and multiplying them together. We're going to take alpha, which is a
Greek letter.
The number.
okay, it's a Greek letter, okay, but it's going to stand for
The alpha for real numbers.
real numbers. Guys, just because it's Greek doesn't make it hard. A theta so beat the hell out of you. You think anytime anything's written in Greek, it means it's impossible. Okay, because of Gutenberg, they used letters for variables. But we could use emojis. We could call it smiley face. Smiley face is an element of the real numbers. Or we could call it something you like Klein's ice cream cone. We could say Klein's ice cream cone is a element of the real numbers. But we're not going to use emojis. We'll use letters. So we'll just say alpha. It's a symbol that represents something. And A is an element of
A vector.
our vector space. What the hell does that mean? I hate you. Dr. Warren, don't do this. If A's in V, then A's A. This is for the third time today. If A's in V, then A's A. Order triple of
Real number.
three real numbers. So we're going to define a multiplication, the scalar multiplication. The real number alpha times the vector. The real number alpha times the vector A, which means A times this ordered triple of three real numbers. Agree or disagree? By the definition, that's what that would be. Agree or disagree? Thumbs up or thumbs down? Thumbs up or thumbs down? Okay. Now, question. What do you want it to be? You think about it. You're taking a real number and you're multiplying it times a vector. What do you guys want the result to be? Because it doesn't make sense. You got a real number and a vector and you're multiplying them together. What do you want it to be? I mean, it could be an imaginary number, it could be a real number, it could be a vector. What do you guys want it to be? What do you want the result to be?
A vector.
How many people are going for vector? How many people want it to be a vector? Okay, so I'll go with you. Let's make it a vector. Well, then it's a...
Real number.
Okay, so that means I need three real numbers in an order. Now you guys are going to be the creator. You've got to have a real number here, a real number there, and a real number there. Write down what you think. Write down what you think. What do you think? What are you gonna pick as that first real number, that second real number, and that third real number? Write it down. Write it down. You're essentially making this. You're essentially making this up. You're going to take a real number times a vector. I guess before we do that, let's just go. Give me a real number, guys. Give me a real number. I heard 5. I heard 5 and I heard 2. Now give me a vector.
2, 1, 3.
2, 1, 3. Okay. Thank goodness we have more numbers than that in the real number system. Okay, now you said I want the result to be a vector. That real number times a vector is going to be a vector. What do you guys think? I mean, what would you make that first one? I mean, if you're just defining this, what do you think?
10.
That seems pretty obvious. If it has any merit, we don't know. How about this? What would you call that? How about that one? 5. And how about this last one? 15. Okay, let's go with that. Let's go with that. Extending that then this would be the real number. This would be the real number the way you defined it. This would be the real number alpha A1. And then I'm just going to jump ahead, alpha A2 and alpha A3. Right now, guys, we have no idea if our addition or our scalar multiplication has any purpose whatsoever. We're just making it up. And that's what's beautiful about math, guys. You can make up this stuff, look at all the different kinds of properties, and then you hope and pray that it actually has some merit. You have to hope and pray that it actually has some purpose. Okay, let's talk about equality. Has equations been useful so far in everything you've done in math, in physics, and chemistry? Has it been useful to have an equal to sign? Has it been useful to have an equal to sign? Okay, let's talk about two vectors being equal. Let's talk about two vectors being equal. Vector equations. Let's talk about vector equations. Okay, the vector A equals the vector B. For the 7th time, if A is a vector, then it's a what? If B is a vector, then it's a what? And we're going to say that this vector is equal to that vector if and only if. Guys, I'm going to introduce some new notation to make all of our lives a little bit easier. IFF. Guess what that's going to stand for in this class? IFF. It's not if and only if. How many people are willing to accept if we write down IFF, it stands for if and only if, so I don't have to write, you don't have to write those words over and over again. So let's do that. If and only if, okay, now you guys help me out. We're saying two vectors are equal. What do you think? What would you make the natural consequence? If this vector is equal to that vector, what natural consequence, what would you say? That's true if and only if what? That would be true. This ordered triple of three real numbers is equal to this ordered triple of three real numbers if and only if what?
A1 equals B1.
If and only, that makes sense to me. A1's got to be equal to B1. Are you done? Are you done? Is that the only component that needs to be equal? Also, are you going to force?
B2.
And then
A3 equals B3.
A3 equals B3. A3 equals B3. Okay. We have our definition of a vector space. Stand up. You're in your video game, you're going to face your first monster. So stretch. You're going to need to stretch to face this monster. Okay, look at something that tells time. What time is it? What time does class end?
10:55.
Okay, sit back down. Math is proof. Here we go, guys. First proof. Now, guys, I'm not proving everything in this class because we'd never get anywhere, but you are going to make some proofs. You're going to realize that this thing is built on the most solid of foundations. This is built on the most solid of foundations. Okay, you're like, Dr. Warren, I like where we're going. I think I've got this. 5 plus 0 is 5. And that's by our algebra of the real numbers. Okay. I've got a vector A. I've got an addition defined on my vector space. Do we not have that now? Can anybody think of a vector that would work like the additive identity for a vector space? Which would mean, like 5 plus 0 is 5, that the vector A plus the vector 0 would result in the vector A. Is there an additive identity element? Can anybody think of a vector, an ordered triple of 3 real numbers, that under the addition you defined would leave the identity of that vector alone?
0, 0, 0.
How about 0, 0? Write that down, write that down. Write down your vector 0, that's 0 squiggle, equals 0, 0, 0. So here's our theorem. A theorem is not a definition. Definitions we accept, theorems we prove. This is going to be our first proof. Now you guys read it. What does that say? Read.
Theorem.
Theorem. Theorem. That's laziness for theorem. Could you spell that, Dr. Warren? Theorem. You'll recognize this as sadness. But it's really happiness. It's really happiness. I'm rewiring your brains to think in new ways. So here's our theorem. Now you guys help me out. Read. You should be able to at least read it. Vector A,
Plus vector 0.
as you defined it, 0, 0, 0, that ordered triple, is equal to the
Equal to
vector A
for every
for every
vector A
in the elements of our vector space. Okay, guys, let's prove this. Do you want to prove it or do you want me to prove it?
Where do we start to approve
Yeah, I guess that's a good question. Pierre goes, where would we start? Okay, so maybe I'll take this one. Is it okay if I take this one? You promise to help me. You promise to help when I ask questions. You promise not to just turn off your brains and write and not think about lunch and not think about your friends or think about anything. Forget your boyfriend, your girlfriend. How many people are going to follow Dr. Warren and think with Dr. Warren? Raise your hands. Okay, you're lying. You're lying. Okay, so here we go. Okay, proof. Given A is an element of V. That's what we were given. Given A is an element of V. It's an arbitrary element of V. You could also say let. You could also say let. Now, what did you pick your vector 0 to be? You guys chose it. You're trying to show it's an additive identity. What did you pick it to be? What did you pick it to be?
0, 0, 0?
0, 0. Okay, you said you were going to think with me. What have I written? You guys said you were going to think with me. What have I written?
There exists.
Then there exists read that to me, read that to me.
A1, A2, A3, elements of real numbers.
Such that the vector A is equal to, now you guys promised you would think, the vector A is equal to, you guys do it, help me out now. Help Dr. Warren out.
Of A1, A2, A and A3.
Okay, we've written that down. We got to provide a justification. My justification is by my definition of my vector space. My justification is by my definition of my vector space. I can't wait till you guys get in class so I can write smaller. So now I'm going to put my justification. I'm going to put my justification, and you guys are going to write down the logic. My justification is by substitution on V. Substitution on my vector space. Since A is equal to A1, A2, A3, that order triple, and 0 is equal to 0, 0, 0, then A plus 0 is equal to A1.
1, 5 plus 0.
We're not there yet. We're not there yet.
Plus 0.
0, 0, 0. We're just substituting. We're substituting two things we've said were equivalent. A is the same as this. 0 is the same as this. And now we're doing that. How many people are following the proof? How many people are following the proof with me? Pierre, are you good? Zach, are you with me? Are you with me so far? Okay, so now. This vector plus this vector is that vector. What's your justification? What's your justification? What are you guys using? What are you using?
Closure of addition.
It's not closure of addition, but I like you going after it there. It's our definition of, who defined vector addition in this class? Vector addition. So we can get away with just writing V plus. It's by our definition of vector addition. Didn't you guys say you just add the components? Isn't that what you just said? And you said that's what we're going to do. We're going to make it the vector where we add the components. Okay, but this is A1, this is A2, this is A3. And because it's COVID, I'm not going to have you say by the additive identity property of the real numbers. I'm going to let you get lazy and just say by the algebra of the real number system. Do you remember that sheet I shared? Do you remember that sheet? I almost said a bad word. Do you remember that sheet I shared? All those properties, whenever you use any one of those properties, transitive, less than's, greater than, you can get away in your justification by writing ALG, real numbers. How many people like me? How many people are happy? Say thank you, Dr. Warren. Say thank you, Dr. Warren. You may hate me later when somebody goes, what's the additive identity? And you're like, I kind of forget. If Dr. Warren would have made you remember, but I'm just going to say, no, we're just going to remember to do our live safe. We're just going to remember to do our live safe. Okay, now I'll write down the justification by substitution in our vector space. What is the order triple A1, A2, A3 equal? What is the order triple? What's the same thing as the order triple A1, A2, A3? Vector A. Now notice what we just proved. Notice what we just proved. We just proved that A plus 0 is A plus 0 is A plus 0 is
Vector A.
the vector A. We've just shown that A plus 0 is A. Isn't that cool? And you're like, no, Dr. Warren, that's not cool. No, guys, it is so cool. How many people knew that the vector, how many people took physics? How many people knew that like A plus 0 was A? If you have a vector plus 0, the 0 vector, you get A. If you have a force and you add something that has no force, you're going to end up with you're not going to change the force. But guys, that's not math. That's not math. Yes, forces is a wonderful application of vectors, but it sure the hell isn't everything. Okay, what does this symbol stand for? What does this say? What does this say? Read this to everybody. Algebra of the real numbers. Has it been nice that like 2 plus 3 is the same as 3 plus 2? Has that been nice? Has that been nice? Has that been nice? Has that been useful?
Yes.
Do you think we could prove that vector addition's commutative? No, Dr. Warren. Do you think we could prove that the vector A plus the vector B is the same thing as the vector B plus the vector A?
Yes.
Okay, go ahead, try it. And then I'll help you out with the formal proof. Try to lay out the foundation. Here I'll help you out. You're given this. A and B are elements of V. I want you to show A plus B is equal to B plus A and justify every step along the way. Okay, hold up what you have. Hold up what you have. Whatever you've got, I want to see it. Hold up what you have. Hold up what you have. I want to see what you got. You're like, Dr. Warren, don't make me do this. No, hold up what you have. Hold up what you have. You'll be happy when you look. Hold up what you have. Look around. See what other people are doing. You see, a lot of people are breaking into components. I'm seeing lots of good things. Ian, I'm liking where you're at. You're justifying. Look over here at Ian's. Look over here at Ian's. Hold it up. Ian, am I butchering your name? I just butchered the hell out of it. Do you see how he's providing justifications? Do you see how he's providing justifications? He's making a proof. He's making a proof. Now, are all these correct? Okay. We'll sit back down. Okay, now, here I go. Can Dr. Warren take over? Can Dr. Warren take over? Guys, remember, it's surfing. You're surfing with me. It's okay to not understand. Hands on the space bar. Hands on the space bar. Hands on the space bar. Say that. Say what I just said.
It's okay not to understand.
How many people have done a sport before? How many people have done a sport before? How many people were competing in a sport? Did you not understand that sport in the beginning? Did you not understand that sport in the beginning? Did you look like a fool playing that sport for a while? Do you guys remember that? You remember learning how to dribble? Oh my gosh. How bad that looks. Who's gone to a little kid's basketball game before? Who's gone to like a little kid's basketball? Is that not some of the worst basketball you've ever seen in your life? But isn't it beautiful seeing them play? Isn't it beautiful seeing them play? And it's just like that for you guys. It's just like that for you guys. It's beautiful seeing you write these things down. How many people realize this isn't going to go away in this class? How many people realize this isn't going? How many people realize Dr. Warren is the placenta? Say that.
Dr. Warren is the placenta.
How many people understand that why I have that attendance policy, why I need you in class to be successful? Okay, so now I'm going to help you out. I'm going to help you out. You guys really were doing quite well. You guys were really doing quite well. But I'm going to start out, and I'm just going to fill in the details. I'm going to fill in the details. Let A and B be elements of the V. Then there exists, a lot of you guys didn't get your players on the soccer field. You got to bring your players onto the field after the national anthem, whatever that means, okay? You bring your players onto the field before you start the game. And so this is what we need to do. We know we need components. We know we need components. But you're an element of V if you're an ordered triple of real numbers. So let's get those real numbers on the field. Then there exists A1 through A3, B1 through B3, and all 6 of those guys are what? All 6 of those guys are what?
Elements of a real number.
So let's say that. Such that the vector A is equal to what? You have this A, but it's not in component form. This vector A, help me out, guys, help me out.
A1,
A1,
A2,
A2,
A3.
How many people are following? How many people are in the game? How many people are surfing? So let's start here. Let's start at A plus B. We know we're done when we reach what? We're going to start here. Now that we've got everybody on the field, we're going to start at A plus B. We know we're done when we reach what? We know we're finished the argument when we reach what?
B plus A.
B plus A. We know somewhere over here, we have to reach B plus A. And just like Ian, we've got to justify every single step along the way. Oh, I didn't. And guess what Dr. Warren didn't do? Guess what Dr. Warren didn't put down the justification. I'm just saying, oh, A and B are in V, there exist these real numbers such that. But Dr. Warren didn't give a justification. And nobody called foul. Nobody in the referee, you guys were referees, should have gone, foul, blow your whistle. Woo! Blow your whistle. Woo! Say foul, raise your red card, raise your red card. Red card, this is a major red card. Go, why? Ask.
Why?
Ah, shoot, I forgot. By definition of my vector space. That's why those real numbers exist. It's the way we define my vector space, by definition of V. And I will red card you like you red carded me on a test or a quiz, Okay, now now I'm following Ian. Ian's like, wait, this is A1, A2, A3, plus B1, B2, B3. No red card. What's your justification, guys? What's your justification for that? What's your justification? What am I using there? Substitution, so write down by subs of V. By subs of V. Okay, guys, I wrote down the justification. What's the justification, guys? Can you read that? I know it's hard, but what's the justification? Vector addition. This would be equal to what by vector addition? Write it down. Ian had it. A lot of you guys had this. But by using your definition of vector addition, what vector would A plus B be equal to? And what do you have as the first real number? In your ordered triple? What do you have as the first real number?
A1 plus B1.
A1 plus B1.
And then I'll just keep filling this in. Okay, now comes the hardest move in the whole proof. This is when you almost get killed by the wave. Okay, you're here. I want to get to there. What am I going to need to happen down in here, guys? If I want to start inching back toward landing this thing on the beach?
A1 plus B1.
Yeah, I need to flip these guys. This is subtle, guys. This is important, though. Okay, it's been an hour and 5 minutes. My attention span's like 10 minutes. So I know you're beaten up. I get it. You're beaten up. Sarah, how are you doing? Okay. Thomas, how are you doing? Okay. Are you guys with me? Are you guys with me? Are you with me? I pity any other human being that has to listen to this lecture other than you. If you're in some space and some other person's having to listen to this, they got to be like, what the hell is that class? Okay. A1 and B1 are what, guys? Real numbers. Do we have a commutative property on the real numbers? Do we not have a commutative property on the real numbers? Is A1 plus B1 the same thing as B1 plus A1? And guys, that's the trick. You get it to a place where you can use your properties of the real numbers. In these arguments, that's always the trick. Get your players on the field, they're real numbers, get them together as a single vector, and then use those properties of real numbers. So my justification is going to be, now what does that say, guys? What does that say? Read that to me. Read that. What's my justification? So what vector would this be equal to by using my algebra of the real numbers?
B1 plus A1 plus A2 plus A2.
Now there's something that I'm adding, but I'm not going to make you write it down. We're also using our definition of equality on vectors. You didn't listen to all of what I said anyhow. Two vectors are equal if and only if their components are equal. Say that. But guys, isn't this the same as this? Isn't that the same real number? And so that's the way we're doing this, but you can just get away with by algebra of the real numbers. Okay. There's just two more steps, guys. There's just two more steps, and we've landed this thing. Okay. My next justification is what? My next justification is what? My next justification is what? And my final justification is going to be by substitution on my vector space. By substitution on my vector space. This vector is the same as the sum of what two vectors? This vector is the same as the sum of what two vectors? Aren't we using your vector addition? You guys defined it. Aren't we using your actual definition of vector addition? But back here, we got these guys. A is this guy, B is this guy. So substituting, can I substitute this guy for B? And can I substitute that guy for A by what we had over there? Dr. Warren, this is worthless. Why the hell are we doing this? Guys, you just don't get it. This is what math is. This is the most important thing. This is more important than any application of motion. This is the most important thing. Dr. Warren, it hurts. I don't like thinking this way. I don't like making these connections. Guys, if you apply this to any of your subjects, and more importantly, later to your job, you're going to be better at it. Because we eat so many French fries, I forget what percentage of us will have to have, well, it's less now, but open heart surgery. Have you ever heard of open heart surgery before? The first thing they do is cut your sternum. It's called open heart. How many people would want their cardiac surgeon not to be able to produce a proof? How would like at step one they go, cut the sternum. No justification. Step two. Anybody know what we do next? Is that what you would want? Is that what you would want? No. You would want them not Googling. You would want them to say, oh, well, wait. I know I'm going to need components. Let's get them on there. Oh, this is by the definition of a vector space. Oh, we're going to start here, and we're going to finish our surgery here. And look, this step is going to lead logically to this step, which is going to lead logically to this step. And I can justify every single step along the way and reach the conclusion I want to reach. Wouldn't you want your lawyer, your surgeon, your doctor, your engineer to do stuff that way for you? Isn't that what you would want? Where do you learn that skill? Math. So put your hands on the space bar, okay? Put your hand. Say, Dr. Warren, please teach me how to prove things. I know you won't say it with any conviction whatsoever, but say that again. Please, Dr. Warren, teach me how to prove things. I know you don't mean it. Okay. But guys, I'm going to write down some properties. I'm going to write down some properties of the algebra of our vector space V that we can justify, that we can prove. They're not given to us. We can prove it. As I write these down, I'll come back and ask, do you think you'd have a shot? Do you think you would have a shot at justifying these? Here's some of our properties. For the last 5 minutes, that's all I'm going to do. I'm just going to write down some properties. That there's actually an associative property. It doesn't matter which order you add these together in, that the vector A plus the vector B plus C, you get the same vector if you add A and B together. How many people think that's true? How many people think that is true? How many people think they might have a shot at proving it? The problem is it takes a lot longer than the commutative, because how many vectors do you have? 3. So you gotta have 9 real numbers. And there's a lot more stuff getting there. It's about twice as long. We're not doing it. Just like with 5 and negative 5, there's a number that you can add to a vector that you'll get 0. The 0 you pick. How many people believe that? How many people believe that they could justify that there's a negative A? There's a negative A. And like you guys picked the number 1, 2, 3, sorry, the vector 1, 2, 3. How many people picked the vector 1, 2, 3? What do you think the additive inverse would be for the vector 1, 2, 3 that under your addition would get you back to your 0, 0, 0?
-1, -2,
How about -1, -2, -3? Would that work? Would that work under your addition to get back to your 0, 0, 0? Okay, is -1 a real number? Is -1 a real number? So is -1, -2, -3 actually a vector? By our definition of a vector. Okay, just saying these things. Scalar multiplication. What do you think we can show 0 times A is? Now focus. What did you guys pick a scalar times a vector to be? What was the result of the product? You guys picked it. What did you choose it to be? A vector. What do you think we can show the real number 0 times A is equal to? The vector 0. Do you think you could prove that? Do you think you might have a shot at proving that? Do you think you might have a shot at proving that? One times A. What do you think you could show 1 times A is equal to? What do you think you can show 1 times A is equal to? The vector A. So this is sweet. 1 is a multiplicative identity here too. The real number 1, okay, you don't care. Just leave it at that. Okay, how about this? This is fun. How about if you did alpha times A plus B? This is your favorite property. What do you think you can show this is equal to? What vector do you think you can show this is equivalent to? Yeah, your distributive property. It's even better. There's two distributive properties. You also have, you're like, Dr. Warren, that's the same thing. No, it's not. This is a vector plus a vector. This is a, help Dr. Warren, this is a number plus a real number times a vector. Guess what you can show that's equal to? Guess what you can show that's equal to?
Alpha vector A, beta vector A.
How about A minus B? How about A minus B? Should that be well defined? Has subtraction been useful for us? Has subtraction been useful for us? Okay, this is the definition of subtraction. It's A plus negative B. That's our definition. That's our definition of subtraction. A plus negative B. Guess what we can show this is equal to when we're ending class with this? Do you think you might have a shot? Do you think you might have a shot at showing if A minus B is equal to A plus negative B, that's the same thing as A1 minus B1, A2 minus B2, A3 minus B3? I can't prove all of this to you, or we'll never get anywhere. I wish the entire class was chapter 12. I would spend the entire course on chapter 12, making you justify everything. You would begin to really get comfortable with it and enjoy it. How many people like knowing when something's true? How many times when they write down equations does it piss you off that you can't really understand why they're true? And then you're just memorizing, and then you forget which order things are in. I don't want to do that in here. I'm gonna sacrifice some content so that you guys believe stuff is true. Okay, we've laid our algebra, but what was Hamilton's goal? To create an algebra for geometry. Guess what we're going to do on Friday? Yeah, we're going to see how our algebra can be used in geometry. It's sick, guys. It's sick. Okay, you guys are great. You guys are a great class. I can tell this already. You guys focus much better than your teacher. You're in the game. You're playing with Dr. Warren. You're out here on the court, actually in the field. This is going to be a great class. This is going to be a great class. Okay, work on your WebAssign. Work on your WebAssign. I didn't pick any of the physics problems. Hopefully you can get a little bit better. Certainly after we do some of the geometry, it'll get a little bit simpler. How many people have started the WebAssign? How many have started the WebAssign? Okay, read 12.2. Read 12.2. Remember, you can't type IJ and K in. You cannot type IJ and K in on WebAssign. It'll just it'll give you a red card. It'll give you a red card. Okay, you guys are fantastic. I cannot wait to see you on Friday and really see you in the classroom on Monday. Okay, thanks. Have a great day. Be safe. Be safe.
Thank you.
Thank you.
I have a question.
Yep, Nick.
So I live on campus, and I was supposed to be moving in on Sunday, but I'm told that we're supposed to be getting a ton of snow up in Harrisonburg, and that could possibly affect move-in. So if move-in does somehow get pushed back, or if I can't make it up to Harrisonburg, what would happen?
Chances are, if we get a ton of snow, they're just going to cancel the university. Chances are we won't have class that day. So then you would our next class would be on Wednesday, and you would move in then. I mean, you would move in, and then our next class together would be on Wednesday. Does that make sense? So it'd be like a good old-fashioned snow day. Even though I'm not sure after COVID that'll ever exist anymore. They'll just call it virtual day. They'll call it virtual day. But I'm believing it will be an honest-to-goodness snow day if they cancel. So if I may go virtual, but I probably wouldn't. I'd probably just give you guys the snow day. Because I need the board. I need the board to teach.
Yeah, that makes sense. All right, thank you.
All right, Nick.
See you on Friday.
See you on Friday. Good luck with moving.